Okay, am I scooching for a second? Okay, hi everyone. We're going to be getting started now, but real quick, thank you everyone for coming. In case you don't know, this is IEEE EMBS, for like Engineering, Medicine, and Biology Society, and we host a lot of events like this, inviting like distinguished lecturers. So today we're going to be having Dr. Eshraghian give a talk on neuromorphic neuromodulation. Just to give a quick biography, Dr. Eshraghian is an assistant professor and Fulbright scholar in the Department of Electrical and Computer Engineering at UC Santa Cruz. He's a developer of Estin and Torch, a Python library for training spiking neural networks, and he's a dual-appointed IEEE CAS and EMBS distinguished lecturer, an associate editor of APL Machine Learning, the chair of the IEEE Neural Systems and Applications Technical Committee, has been a recipient of 7 IEEE Best Paper Awards, a scientific advisory board member of BrainChip, and leads the neuromorphic agents team at Quantum. So thank you so much for coming to speak to us today with all of your accolades, and I hope everyone has a great talk or listening to you talk. Okay, thank you.
Yeah, I wouldn't mind it if everybody else had a great talk. I'm more than happy to sit down and listen to you. And Katie, thank you for that introduction. I hated myself with every word more and more. So for those of you that are here for the second hour of me yapping, I'm so sorry. 10 a.m. we talked about neuromorphic LLMs, and now we're going to move over to the small scale systems where we want to take a pre-existing workload and try and make that a bit cheaper. So yeah, this talk is really about the computational methods that enable workloads that would simply just not be very possible if they weren't squashed into the milli or microwatt regime, as opposed to the language models where the more compute you had, the better. So it is largely computational, and while I am personally extremely far from a voice of authority in neuroscience or biomedicine or biology, yeah, you want me to talk a little more? This is turning into an ASMR show. So we're going to be talking about, is that what we want? What am I doing? I'm none of these things. I'm not a clinician. Actually, the video is going to be like my neck if I'm this close. But yeah, it turns out that neuromodulation is a pretty good domain to apply some of the learning rules that we've come up with. In particular, there's going to be a big focus on closed form systems. And yeah, give me a shout if Zoomland can't hear me or anything. What I want to get started with is a story from 3.5 years ago. UC Santa Cruz made the mistake of hiring me, and I moved from Australia. My driver's license from Australia didn't transfer cleanly. The DMV doesn't recognize people that drive on the wrong side of the road. So I had to take the bus to the office every morning and going back every evening. So this was my view from that bus. It's a couple minutes away from my office. It's not bad. It's pretty good. Actually, day one, I was astounded. I thought, holy shit, this is incredible. This is remarkable, right? Day two, still remarkable. Day, I don't know, 700 and something. Jesus Christ, I've got to grade all these assignments. I have to do a bunch of NSF project reports. I need to schmooze to this company and tell them that I'm going to do all this work. Great. I need to bring funding for this student. Oh man, this student's not performing. Or maybe I'm just not seeing that. Anyway, stress, right? Your brain is a little bit occupied. You stop taking in all this beauty. Where am I going with this? Now, if you're exposed to the same things day in, day out, your brain starts to figure out what it should expect, right? And in absence of any surprises, you could think of your brain as going into some sort of low power state that generates the surrounding environment that you're going to be in, right? And let's say that a mountain lion, which apparently do exist here, a mountain lion jumps out of nowhere and does come into my field of view, then I update my model of the world around me, right? And it seems like predictive coding does lean into this a fair bit, where your brain is only going to allow for sensory inputs to be passed and to be processed if there is something worth processing, if there is some sort of surprisal. So starting with this idea, I'm just going to go straight into this, right? How can we leverage these kind of weird and somewhat wonderful ideas into making learning a bit more effective? I'll take it straight into neural forecasting, right? And the setup is something like this. Take a set of EEG signals. You're recording, you're transmitting a bunch of these waveforms into a pair of neural networks. One of them is a detection model. The other one is a forecasting model. The detection model takes these various channels of EEG and it's trying to tell you, is there a seizure going on right now? The forecasting model has a tougher job. It's trying to tell you, given everything I've seen, will there be a seizure in, say, 30 minutes? How might these models compare against each other? Are they competing? Are they conflicting? Or can they work together? Now, in the forecasting case, you could argue that this is perhaps a little bit more useful. It enables some sort of preventative measure, right? If you know in advance that there's going to be some sort of adverse event, you can close the loop, stimulate, you can tell someone to stop driving, you can take preventative measures. But it's difficult. It's harder to tell you what the weather's going to be in 30 minutes than what the weather is right now. Yeah. A detection, on the other hand, it's pretty much as good as it gets. Given some EEG signals, telling you what's happening with those signals right now is the best that I could possibly do. So what's the setup? How are we taking inspiration from predictive coding here? We recently published this paper called Future Guided Learning, and it goes something like this. Hopefully this animation works through Zoom. You're moving forward in time, and then suddenly this detection model is going to say, ding, 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 there is a seizure. But the problem with this picture is that 30 minutes ago, that forecasting model should have lit up, right? And in the event of a mismatch between these two models, then perhaps we should use the detection model to update the forecasting model. That's conceptually quite simple. And I think that we could all appreciate that the detection model is probably as good as the forecasting model will ever get. And maybe that's why you don't want to rely on ground truth signals to updating the forecasting model. Sure, you could strive for 100% accuracy, but if your detection model isn't able to reach 100%, then maybe we're comfortable with sacrificing, that final 5% or so that the detection model can't do. So we aim for the same error rate as the detector. There are a bunch of upshots on this as well. Given that you have a pre-trained detection model, and there are plenty of detection models out there that do reach neurologist performance for these types of tasks, you can treat that as the system that generates labels. So you no longer need manual labels. That's nice. This forecasting system can effectively become patient-specific, and that becomes quite important because different patients are going to have, I guess, different neural signatures, as many different types of epilepsy, different types of seizures that stem from different brain regions. And so having a forecasting model that is continually adapting and updating to one individual patient makes a lot of sense here. And if we want to quantify it a little bit, you get the highest area under your receiver operating characteristic curve. For those of you that may not be so statistically minded, it's effectively a measure of accuracy that accounts for imbalances in your data set. We swept this across individual patients, a variety of individual patients. On the y-axis, you have your surrogate for accuracy, your AUC-ROC. On the x-axis, we're just sweeping across a few different patients, and don't worry too much just yet about the many, many different bars. We're comparing three different models in light blue and in, I guess, light red. We have the previous state-of-the-art forecasting models out there, and then in green, we have future guided learning, this technique that we proposed. And we swept across different patients. We swept across different data sets to ensure this all generalized. So CHB, MIT, and the AES data sets. This is pretty messy. Hopefully, we're all comfortable with me just averaging some of these out. And ultimately, you do see a significant boost in performance over what was previously state-of-the-art there, at least for one of the data sets, and the other one a slightly marginal increase, which perhaps indicates that maybe that's a relatively easy data set to solve. So that's all well and good. That's nice. The takeaway is that we can minimize surprise by learning from the future. But let's be a little bit more pragmatic about this. What's the cost of running something like this? If I am a patient with chronic epilepsy and I want a device there that's consistently observing me, that's continuously being trained, how expensive is that? What are some of the drawbacks of something like this? So on the one hand, you could argue that there's some sort of cheaper training cost because maybe you only train at mismatch when the detection and forecasting models diverge from each other. And we've done a few different tests, right? We've done tests where we do not train at just mismatch. We train at every case because really you're not generating yes, no seizure predictions. You're generating logits, right? So even if both models say, yes, there's a seizure, maybe the logits slightly diverge. And you can keep updating those, right? Alternatively, you could just treat it as a black box and you say, I'm going to treat my supervisory signal as a binary yes, no that comes from my detector. In this particular paper, we went for the logits. That feels like there's a bit more information to glean from there. And so this point does not hold true. You are learning at mismatch. You are learning even when things match, right? The second issue here is that you've got multiple models being deployed in one hit. Sure, maybe your detector and your forecaster are relying on similar base features, and maybe you could share part of these models, and we didn't test that. I think there's an interesting question there in sharing some of the layers between these models. But one question that we might ask is, how can we make on-device training cheaper? If we have to train things as we go, if we need to personalize a model, then perhaps we want to make it a bit cheaper. So I want to get everyone on the same page here and discuss backpropagation through time, this learning rule for basically every sequence model that's out there. What's the deal? So here I'm showing you a recurrent neuron. This is if we replicate this several times and we put this into a larger scale network, then you have a recurrent neural network. One of the first issues with backprop through time is, well, if I unroll the computational graph across multiple steps, then you might ask, how is this biologically implausible if you care about that? And I think to some extent we should. So firstly, we have the spatial credit assignment problem, which effectively asks, how does a loss propagate the blame to a weight that is spatially far away? Right? In a computer or in a GPU, we know exactly how each weight contributes to some output loss. We then apply the chain rule by backpropagating through this graph. Every chain rule calculation might have some extra bits that describes its destination. It knows what weight it needs to go to. The gradient knows where it needs to go to and effectively update. Is this a mechanism that can take place in the brain? It's plausible that your brain might calculate errors, but can it store a memory of every single wire it took to generate that error? Almost definitely not. Maybe an approximation of it, but almost definitely not. And we call that the spatial credit assignment problem. The next issue is the temporal credit assignment problem. So backpropagation through time goes back in time to calculate gradients. And we see this traversing back the unrolled computational graph. This implies that all of the states throughout the history of the forward pass need to be stored in order to run backprop through time. So not only does it sound ridiculous to think about our brains having a perfect memory of everything that's ever happened to us. God, I would hate that. But in silicon, you can consider this to be painful as well because there's a memory complexity issue. Memory is expensive, and this just exacerbates that. So where do I want to go from here? I want to be able to address some of these issues, present alternative learning rules, some of which have failures, some of which have wins, and then loop it back to how they might affect neuromodulation. A logical approach might be to start with backpropagation and remove certain pieces of it such that biologically plausible variants can emerge from it. So let's decompose backprop through time. And forgive me, you're going to see a slide deck with a disgusting amount of math. I think it's necessary to really come to an appreciation. Got psyched. I think you need it to gain an appreciation of what the solutions entail. But what I'm going to show you is just backpropagation pathways, just a ton of chain rules, right? The first set of pathways will be what I call the immediate influence of the weight on the output. In other words, how does a weight at t equals 1 influence the output at t equals 1, right? How does a weight at t equals 2 influence the output at t equals 2, and so on and so forth, right? And then you can probably see that, we've got a few other forward pathways and we need to traverse through those as well. Once my slide deck catches up. Not yet. My slide deck is frozen. Let's let it catch up. But what you're about to, there we go. Okay, wonderful. So we can move on to the influence of the weight on the output after a 1 time step delay as well. How does the weight at t equals 1 influence the output at t equals 2? My laptop's really struggling with this setup. Okay, but you get the spirit, right? You can kind of see how animations really screw up with Zoom, but you can also see how the backprop pathways are going to vary across timescales. And you probably can guess what the next slide deck is going to show you. You're going to see the backpropagation pathways that traverse longer and longer timescales. And so in that picture, I wish you could see my screen right now. It's really having a hard time. The influence of your weight on your output after a 2 time step delay. And once the animations catch up, you're going to see the output effectively traversing back 2 time steps, right? And so all of these terms, things that I need to figure out, how can I calculate these without storing everything in my memory, right? That's really my goal. As you run longer sequences, as your context grows, as you let things run, the pathways get longer, the chain rule expression gets longer, the amount of memory you use really gets exacerbated. So the problem I want to solve here is the temporal credit assignment problem. So in backprop through time, I need to complete my full forward pass. I need to unroll the full graph. I store every one of these terms during my forward pass. And then I calculate these chain rule terms that you're looking at in order to do my weight updates with whatever optimizer that you prefer. That obviously breaks real world constraints on temporal credit assignments because our brains cannot, unfortunately, go back in time. So the next goal is breaking this up into a more biological plausible variant. And this solution is called real-time recurrent learning. The goal is to run a training algorithm that looks like backprop through time, but you do it using only the information that is available to you at that current time step. You can be a little Markovian about it and also account for the previous step if you wish. That's okay. You're allowed to push information forward 1 step as long as you do so without expanding memory over time. Yeah, technically you could push every single variable forward, but then you need to allocate a dynamic amount of memory as you run that. So I'm going to run a forward pass through my model and also run a backward pass. So what does this look like? I'm able to run the immediate influence given just the present time step of information, and I can do that without any historical information. That's fine. That's easy. So my first term, clean. These immediate influences, super easy to account for, right? The next step, we're going to move forward 1 step in time, and this just uses the membrane potential update, if you like the spiking neural network lingo, where U1, this hidden state of my recurrent neuron, gets scaled by beta in order to contribute towards the hidden state at the next time step. That gets added to these 2 terms. Actually, you can't see my cursor. That's okay. That gets added to these 2 terms, the product of these 2 terms, right? And we can run a backprop through time step there. So your immediate influence at t equals 2 is also easy to calculate. Happy days. There is, of course, one caveat, though, right? You can see that we've now introduced the need for a 1 backward step delay. This is okay. If I solve this, I get something that looks like, oh, we're freezing up again. I'm partially tempted to just delete all the animations from this slide in the space of like 30 seconds. Because right now I'm like forecasting how long it will take me before oh, we're good, beautiful. I'm projecting, I'm using predictive coding to figure out how long it's going to take me to get to the end of the slide, and I'm clicking that in advance. So as you move forward in time, actually, I think I can do this over here. There we go. As I move forward in time, you can kind of think of the solution to this 1 step delay influence as, the effect of of my hidden state at my previous step on the hidden state at my next step, it's just a factor of beta, right? A simple derivative. So that decomposes to beta, and this final term is just y1, right? It's this guy coming in. That's good. Y1 comes from the previous input, and that first term was already calculated during our immediate influence. So all of this information is available to us. There's no temporal credit assignment that's being breached here. So we get a little bit of reuse of information as well. And my mental model is kind of like this. I push y1 forward in time.
But in this case, you suppose that it's stationary in the operation, but there's no change in time. Or you need to consider the delay in each operation. But
you do not want to have to make any assumptions about the delay in the construction of real-time recurrent learning. The only constraint is that we want to run something that looks like backpropagation through time simultaneously with the forward pass, right? With backpropagation through time, in order to do it cleanly, you need to unroll the entire sequence length, and then you run backprop through time using all of the stateful information you have available to you. In this picture, I'm obfuscating everything in the future and stating that you can only use the variables available to you at the present step and one time step before. So by the time we get to the third time step, that's when things get interesting, because I'm not allowed to access any information from that very first loop unrolling. And something I alluded to earlier was the easiest solution to this would be just pre-allocate a ton of variables and that's it. But that breaks the memory constraint on.
But the reality is that the information is spent sometimes to propagate from one point to the next point.
Yep. I mean, in the case of RNNs, you assume a fixed delta t. So going from one step to another step is going to be constant. And so there will be delays if you go from t equals 1, say, to t equals 10. Then that propagation takes a bit of a longer time, right? But in absence of that, RNNs do bake this fixed time step assumption. Yeah.
The data, if you have a nonlinear activation function, I think the data would depend on time, right?
If you have a nonlinear activation through time, you mean?
Well, if you have here you have activation functions on the like when like at each step, you have an activation function there.
You don't have to. I mean, whether or not you have an activation function through time that precedes beta, that doesn't modify real-time recurrent learning. What it would modify is the ability to train things in parallel in the spirit of state space models. So this morning I talked all about state space models and how they can be parallelized. Here it doesn't matter so much. Yeah.
Because if I remember correctly, like if you have these activation functions, like nonlinear activation functions,
yeah,
this would mean that this beta term is also like inside of the backward through time. At each step, there is this thing that depends on the state at that time.
You're saying that there could be a world where beta. Right. So beta. Okay. So beta. You're saying that beta could evolve over time. Yeah.
Yeah.
Okay. In vanilla RNNs, even with nonlinear activations through time, beta stays fixed. Beta does not change with time. That can be thought of as your transition matrix that stays fixed. But the case where they do matter are architectures like LSTMs and most modern state space models. That's when the transition matrix is a function of the input data. That's when it matters. That's when it changes through time. All of this still generalizes to those cases as well, though. RTRL does generalize to those cases. But it's an interesting point to think about. And in practice, what you just described, this data-dependent decay, jacks your performance up considerably. Yeah. Yep. Yeah.
Why require that beta have to be constant? No.
You don't have to require beta to be constant. No.
See, the beta in the first part is equal to the other one.
Yeah. In the interest of moving forward, I'll probably shut this question down, but very briefly, beta, that can be whatever the hell you want. I've denoted it to be constant, largely for the sake of being able to compress this presentation into the space of 45 minutes. But in practice, it can mostly be whatever you want it to be within constraints. Yeah.
Just move forward.
Yeah. I mean, my slides are preventing me from moving forward, but we'll get there. Okay. So t equals 3, the third time step is where things get finicky, because we're going to run our forward pass one step. We're going to, let's see. Okay, yeah, we're frozen again. You're going to see the forward pass moving up at the very end, one step. You can calculate the immediate influence with relative ease as well. That's going to be a red line that, red arrow that goes from top to bottom there. No laser pointer yet. So that one-step delay influence is no problem. That's going to look very familiar to you, right? We've seen that already. His first term was calculated during the immediate influence, but I hope you can see what the main problem now becomes. Everything here is fine, but what comes next is trying to push and propagate information all the way from t equals 1 over to t equals 3, right? So it's this, it's going to be another highlighted term that's going to come in a moment. So much of this is going to be reused. We don't need to worry too much. But yeah, this influence of W on S after 2 time steps, that's the pain, right? The 2-step delay is where things get questionable because we now need a term that occurred 2 steps ago. I do not want to have to keep storing additional terms with every additional time step, right? So one thing that I'm going to do is, there we go. This term here is the pain point. That's what's going to be difficult. The point that I'm getting at is, sure, you could pre-allocate memory and store that somewhere and then store it for the rest of the time. But the problem is that you're going to have to dynamically allocate a ton of memory at the very start and store everything. That's what we want to avoid. Okay. With respect to this final bottom equation, that first term, this guy, in absence of a laser pointer, that's easy. That was calculated at the immediate influence step. The second term, the influence of membrane potential on another membrane potential, that's also relatively easy. That's just beta. Beta is accessible to you somewhere else. And more freezing up. But the point is that a lot of this can be incorporated into its own recurrent equation. You can basically recast backpropagation through time into a recurrent equation. I think that's a rather profound result. And once PowerPoint lets me do that, then you'll get to hopefully appreciate it yourselves. Now, this final step, the final 2 terms, those come from 2 steps ago. But I hope you can appreciate that term is also just beta, right? That's available to us. That's local because we're reapplying beta. And if beta becomes data dependent, then beta is basically a template that you can calculate as a function of your current input. So it really does beg this question. And that final term is the input from Y1 2 steps ago. So it begs this question, can I compress these historical values into one recurrent equation that is Markovian in flavor? So I'm going to first conjecture or propose an equation that looks something like this, maybe someday. And what you're going to see in a moment, excellent, is a new variable alpha. Alpha at my current step is equal to alpha at my previous step multiplied by my decay rate added to my input y, which is also multiplied by my decay rate. This feels a bit arbitrary, right? It came out of nowhere, but let's see how we might use this. I might also give up on trying to show you how to use this, and potentially, just depending on how the slide deck goes, let you appreciate that everything can be snowballed into this term. Animation worked. Wonderful. So at the first step, we assume that alpha has been initialized as 0. Nope. I kind of think I might give up on this. Yeah, it's 4:30.
So this is the Zipser-Williams.
Exactly.
By the way, we're here at UC San Diego.
Yep.
This was done actually here, right? Was it 40 years ago?
Yep, 1989. I've got a beautiful slide deck that pays homage in the correct way. We assume alpha has been initialized as 0. At the second step, 0 gets fed back into alpha. Now we add beta times y1, right, from that second term. And this is kind of the act of pushing y1 forward in time through beta. That's something that's already happening in one of the previous computations, right? I think the next step is where the thing that we really care about, right? The final term is equivalent to what we need in our 1-step delay, right? It might be highlighting, but it doesn't matter. And that first term, okay, wonderful. Final term is what we need in our one-step delay. And that first term comes from these guys. That comes from our two-step delay. You've effectively compressed all of oh shit, it's 3 terms. Wonderful. Forgot about that. And you've compressed all of this, right? All of that has been squashed into one recurrent equation. Wonderful. So this effectively, if you trust me enough and you trust people much smarter than me from 1989 enough, all of this can really be squashed into one variable. And I can keep doing this. It can generalize across additional time steps. All we have to do is multiply that guy by this term. And that is immediately available to us. So that's not a problem, right? I can take alpha at t equals 3, multiply it by a small piece of the immediate influence, which is the first term on that bottom, in order to effectively get the result that I want. And I'm going to calculate that anyway. So there's very little extra computation. And that way, you might be thinking, how are you getting all of these different equations in just one recurrent equation? Well, that one recurrent equation is basically smushing together these highlighted terms all together, right? So I like to visualize it as alpha basically snowballing all of the historical variables into one compressed form. This means that you've effectively solved the temporal credit assignment problem. Functionally, it is equivalent to backprop through time. You've just had to introduce another variable and modify the sequence of steps that you need to take there. Normally, that explanation would take 10 minutes with the functional slide deck. Wonderful. So what are some of the implications of all of this? Well, we appreciate the backprop through time. Your memory complexity scales linearly with time. Real-time recurrent learning, you've got these partial gradient terms that are snowballed forward in time. This was obviously discovered by me in 2020, but then I did a literature review and was like, ah, shit, Williams and Zipser already did it in 1989. But I feel like if you come up with an idea that someone else is much more brilliant than you has come up with already, at least then you feel like you can potentially even compete with them just, I don't know, 40 years ago. So a very logical question is, why doesn't everybody use it? Why doesn't everyone use it? Well, let's take a look at these two terms down here. Right? If I'm relying on real-time recurrent learning to calculate the gradient, there is the multiplication of a pair of matrices that are both n by n. What does that mean? I have the computational complexity that scales cubically with the number of neurons. Right? That's a bit of a pain. Yeah. Backprop through time, sure. Linear complexity with time, and I've gotten rid of time, but I'm paying the cubic cost. I'm going to come back to that. I want you to plant that problem in your minds for a moment and appreciate that I do have a solution ready for you, but we're going to get back to it. And when we get back to it, I'm going to knock out two problems, because one of those extra problems is, how can we make multimodal deployment cheaper? So I don't know, maybe spiking neural nets are one way to make these things cheaper. And I don't want to go into spiking neural nets in too much detail, especially for those of you that were either at my presentation this morning, but you should hopefully be able to appreciate that spiking neural nets rely on time-varying dynamics and a few different features where if you excite this neuron with input spikes sufficiently, then it's going to generate its own output spike. And if we were to probe this neuron body, then you see dynamics that look like this at the hidden state. Excellent. The benefits are perhaps sparsity. If you have infrequent spiking, then you have infrequent memory accesses in the ideal scenario. You may be able to leverage low precision arithmetic if your spikes are binarized, which isn't a constraint that has to exist. And you have potential ways to compress information in alternative and creative ways over time. I'd say that latter point is less utilized in most of the modern literature, but a lot of low-hanging fruit there. Let me compare a layer of spiking neurons with a layer of recurrent neurons now, in order to highlight how we can solve the real-time recurrent learning issue, right? So with a layer of spiking neurons, you're going to take a series of inputs, feed them into neurons, and you can hopefully appreciate that I've replaced beta with a set of transition matrices, just W superscript 1, 2, 3, right? So the hidden state of each neuron is scaled by that term. At t equals 1, I've got 3 hidden states, 1 for each neuron. That's going to be what I've recast as a diagonal transition matrix, W1, W2, W3 multiplied by the previous step hidden state, with some input added into that. You can see that W1 is going to be multiplied by U1. W2 is going to be multiplied by U2. W3 is multiplied by U3. So perhaps there's a bit of redundancy in this structure, and I could just express it as an element-wise product, right? That's a bit cleaner. They're just a pair of vectors. Hopefully you can see that there's something cheap about this, right? And then we can just increment over time. Happy days. You keep calculating your membrane potential again and again. What does this look like for recurrent neural nets? In the recurrent neural network case, all of the hidden states from all of the neurons in a single layer, eventually, are going to go through a linear projection followed by a nonlinearity and then fed back into the hidden state of those neurons. So your hidden state is kind of influenced in an all-to-all fashion, right? The transition matrix is now dense. Everything influences everything else, right? U1, U2, U3 are all going to influence U1 at the next step. And likewise for U2, likewise for U3. Not just that, but there's also this nonlinearity that comes into the picture, right? Often a tanh function. So let's do a side-by-side comparison between RNNs and SNNs very briefly. On the RNN case, there's a nonlinearity through time, which hurts with parallelization, which I don't really need to go into detail here because it doesn't affect our algorithms very much, here at least. And there's also this all-to-all recurrent flavor. With spiking neural nets, there's kind of a one-to-one recurrence where the neuron's membrane potential only influences its own hidden state or its own membrane potential. So there's more locality baked in there. And as a result, you might expect that it's going to be a little bit cheaper, right? So let's bring back the real-time recurrent learning case and see what happens if we applied it to a spiking neural network, right? These two terms on the bottom right previously were n by n, both of them. But if we were to diagonalize our transition matrix and effectively collapse it into a vector, that final term becomes n by 1. You go from matrix-matrix multiplication to matrix-vector multiplication. And you're going to see that the computational complexity with an S and N can be compressed down to n squared. As something considerably more manageable, this is now a case where we don't need to worry as significantly with respect to the pains of standard RNN complexity. But some of you that are a bit more familiar with this might be able to identify that, well, if you're removing a bunch of parameters in that matrix, in that transition matrix, such that you can collapse it into a single vector, aren't you losing representational capacity? You're removing weights that can be learned. In this simplistic case, I've gone from an n by n to an n by 1 vector of learnable parameters, right? Let me try and convince you why that's not so much of an issue, right? And it comes down to effectively doing a bunch of matrix diagonalization. So the question here is, does dimensionality reduction reduce learning capacity? In a vanilla RNN, just simplifying the equation, removing the nonlinearity, and I vectorize all of my notation, then I get my hidden state is equal to my transition matrix, my dense transition matrix, multiplied by my previous hidden state, plus my input x naught. At the next step, just increment all your subscripts. If we do a substitution of V1 into the second line, and then we expand that guy out, then we see W squared. W squared, expensive, right? That's matrix-matrix multiplication. That's what scales cubically with the dimensions of the matrix. Now with spiking neural nets, or with diagonalized linear recurrent neural nets generally, if I bring everything back, then W squared is effectively just a vector element-wise producted with another vector, right? That complexity scales linearly with your number of neurons. And then if you wrap RTRL around that, the training process is n squared. So you've effectively cheapened the inference cost and your training cost, just moving everything, well, moving inference down by from cubic to linear and training from cubic to quadratic. But the question that I was asking was, does this affect learning capacity, right? Because you have less parameters to learn from. Well, hopefully you can appreciate that. Let's take W. Let's take my dense matrix W and assume that all matrices can, or most matrices can be diagonalized using whatever diagonalization technique you prefer, singular value decomposition, whatever. And that's going to be represented using PDP inverse, right? If I take W squared, the term that I care about, that's the term that's going to keep getting raised by a higher factor, W cubed to W to the 4, as you increase your time steps. You're going to see PDP inverse times itself. P inverse times P results in an identity. That disappears, and I end up with P d squared times P inverse. What's the cost of multiplying a diagonal matrix by itself, right? That can be represented as an element-wise product. That's going to scale linearly with time. So my point here is that you can take a dense matrix that doesn't have that diagonal property initially. You can decompose it into a set of operations. If I want to multiply some input variable by w squared, I can first multiply it by p. P doesn't change with time. P is fixed. D does change with time, but it's cheap. P inverse likewise doesn't change with time. So that can be kind of treated as a pair of linear layers surrounded by something linear recurrent that follows linear complexity. The inverse of matrices can be computationally expensive to calculate. So what the deep learning community came to was just replacing it with something else learnable. Right? Bit of a cheap, hacky solution, but I guess the point is that if you want to increase your learning capacity and not have to calculate the inverse, let's just set another learnable matrix. And it checks out enough. So it's not a proof by any means, but pictorially, what you're seeing is data flow going from bottom up. You've got a channel mixer or just a dense layer. That's P. You've got a token mixer or your RNN layer. That's your diagonalized vector SNN looking beast. That's your D to the N, followed by another nonlinear channel mixer. Compress all of these together, you bring back the same representational capacity of a fully dense RNN. By doing that, you're effectively able to preserve all of the learning capabilities and effectively not lose anything. So we don't need to worry too much about this. So a bunch of you are perhaps familiar with SNN torch. I'm not going to go into it in detail, but the point is that all of these features, these quirky learning rules have been integrated into a library that I developed once upon a time. But I also want to bring back this. So we've addressed the training issue, right? We've addressed being able to do RTRL somewhat on device using a model that doesn't necessarily lose any learning capacity compared to standard dense RNNs. But for inference, I wanted to make these cheaper because I've got two models running. Now, does it address the right problem? If I replace my models with SNNs, am I addressing the right problem? Well, let's break it down a little bit, right? Let's go back to the neuro side. So on the sensing, your brain might be feeding a set of sensors, and maybe you have a neural network that wants to decide, am I sensing something that I should care about? That might be fed into a controller. That may also be a neural network that is saying, should I take action based on what I've sensed? Then you've got a neurostimulator that ultimately will listen to whatever your controller says. And that goes back into the brain in this closed loop system. So on the seizure side, these are pretty ad hoc numbers that can be very, very debated, very much debated. But in general, I want to give you a sense that low might indicate tens of microwatts, medium might indicate hundreds of microwatts, and then high might indicate single-digit milliwatts. So on the sensing side, that's generally going to be medium to low drain. Unless you need a lot of fidelity, then that goes a little higher. On the controller, if you've offloaded all of the decision-making to your sensor, such as, yeah, there's a seizure, and then your controller just has a binary problem, then that's going to be very low drain. And then your neurostimulator, that may be a little bit higher. That might be sitting on the medium drain. And this is in the case of bursty workloads such as epilepsy, where you don't necessarily need to always stimulate the brain. This profile will look considerably different for something like, say, Parkinson's disease, where you may more commonly need to apply a stimulus. And the point is here that the profiles are going to effectively be different, but if you constantly have the need to stimulate, then you're going to have a relatively higher drain on the neurostimulator. The point that I want to make here is that the portions of this diagram that rely on an SNN tend to be on the very low to medium drain, right? It's the neurostimulator that is costing considerably more higher amount. This doesn't generalize to every single case, but it does generalize to many cases. So I want to make that clear. This led us on to, so the point there is that the naive act of just using a spiking neural network doesn't solve all of your problems, right? So perhaps you need to be a little bit more aware with how you optimize. And I like this notion of energy-aware learning, because I guess the brain kind of did something similar. Given a certain amount of resources that are available to us, our brains were forced to optimize around whatever that it had access to. So the setup looks something like this. Take a rat model, really, represented with 80 Hodgkin-Huxley neurons. So a very simplistic model. You feed a neural spiking data into a Parkinson's disease classifier that might be deployed on neuromorphic hardware. That tells a controller what to do. and you go and feedback the decision that the controller makes into the rat. The most obvious reward signal is efficacy. Did you suppress Parkinsonian behaviors? If yes, congrats, reward. The second reward, which is where things start to get a little interesting, is energy or latency, depending on what you care about exactly. In this picture, perhaps we care a little bit more about energy. So what this model is really trying to learn is, how can I suppress these behaviors? How can I suppress, I guess, the manifestation of Parkinson's disease using the least viable energy, right? So the point is that you reward your model for the total energy usage, not just the spiking neural network energy usage. And a lot of folk in the neuromorphic research landscape do get this kind of, it can be very seductive to optimize the number of spikes in your model. But the model is such a small part of your overall system cost. So really baking in everything into that one optimization objective makes a lot more sense. And in practice, you often will combine your controller and your sensing networks or whatever into one single homogeneous entity, as I've done here. So this is the high-level top-level diagram. Don't worry too much about it. This is just an example of how a single episode run will behave. On the top, you have, I guess, your alpha beta power. Typically, you want that below a certain threshold. And this threshold may be independent for different users. And as you go through additional training episodes, the black line does indeed go down below the threshold we care about. On the bottom plot, across episodes, you're seeing how phase, amplitude, and pulse width change on the neurostimulator side before they find a steady state that caters towards an individual parameterized rat model. We tested this out across a variety of spiking neural networks. So in deep blue, you're seeing the average latency, and in teal, light blue, you're seeing the energy consumption. And we're sweeping across various sparsity patterns of the SNN. This ranges across something like 1 to 10%. Honestly, the difference is pretty minuscule. It didn't seem to matter very much. As long as you are using an SNN on neuromorphic hardware, you didn't really need to reward sparsity. You got much further by rewarding the overall system cost, which is kind of fun. But I think there's a lot more that could be done here, right? We're rewarding energy-aware learning in a very specific setup that is very concerned with low power microwatt milliwatt acceleration runs. But what about the large scale? And this is kind of where I'm going to start wrapping up, because going beyond neurostimulation, perhaps you have a chunky language model, and that's the thing that you want to optimize. But your language model perhaps is of neuromorphic flavor, as the ones that I presented this morning. You deploy them on your device, on Loihi, on whatever neuromorphic chip that you have access to. That neuromorphic chip will probably have some power profiling tools. You're able to extract the energy that it takes to generate, to deploy a model. That energy can be fed back into a series of agents, perhaps. And those agents will be ingesting all of that information. And I think code writing agents are now very prevalent, and they can effectively restructure, reparameterize your code for you in far more intelligent ways. And that is effectively what we did. So I want to give you a cute little example, and hopefully these animations work. So one agent might be a training agent where the goal is to reduce convergence time, and that is effectively going to rewrite my model code. Another agent might be tasked with data loader, right? Optimize your data loader. You want to stream batches on chip effectively. So now that's going to be fed into my context of my LLM. And that's going to be the output action that it takes is going to be modifying that language model network that you see there, right? And then the third agent perhaps might be your kernel agent. Use the linear kernel, and I don't know, if it doesn't listen to you, maybe you say, do not use softmax in capital letters. And then you say, I said no softmax. And that's actually a real analogy, because we found that yelling at your language model tends to get better results somehow. So if you open up the code of my student Andrew's work on this, yeah, there's a bunch of capital letters, very, very aggressive, angry capital letters. So how do our experiments look on this setup? These are just very early preliminary results, but I think that this is a super cool direction to go into. But we took the neuromorphic MNIST data set just as a rough example, which effectively takes an event camera, points it at a sample of MNIST, and what you saw here was the number 0 with a moving event camera. Ran this on a RTX 4090, and what you're observing here is just the trajectory of the don't worry so much about the threshold, but on the right, you've got the energy usage on a GPU. Now, energy usage, how do you optimize for energy usage on a GPU? Because there's not much free space, there's not much free parameters, right? Like a neuromorphic chip would have a fair bit more to play with. But in terms of a GPU, what you're seeing is the data loader agent found that if I compress my input data into larger DT windows, into larger batches of time, that effectively reduces the number of sequence steps in my model. And it turns out that this neuromorphic MNIST dataset doesn't have much temporal information. Most of it is spatial. So this agentic approach of having these various models kind of self-discovered that time doesn't matter here. You can compress a lot of your sequence length right down. And so this took a couple of hours to find that result, to compress the neuromorphic MNIST dataset down to below 10 time steps. And if you look at research papers from 2016, when the NMNIST dataset was released, people were using 100 to 500 time steps. It took till about 2020 before people started using sub 10 time steps and were like, hey, this isn't actually that time varying. There's not many important temporal features. So I would argue that this 2 hours far exceeds what it took the neuromorphic community to figure out approximately across the span of 4 years, right? I think that's quite funny. But this is something that we really want to scale up. And this idea of energy-aware learning really came from the roots of neurostimulation, closed-loop feedback, right? So with that being said, none of this work is really possible without the stars in my lab. In particular, this project was, well, the Parkinson's disease project was Bin right here, and the future guided learning work was from Sky right here, and then screaming at a bunch of agents was Andrew. So, I think it's a lot of cool stuff there. Haven't updated the references from this morning's slide deck, but that's fine. So yeah, thank you for spending your Friday afternoon with me. Feel free to yell any questions that you might have. Although people on Zoom, I'm not sure if we'll be able to hear you. We had a bunch of issues there.
Would you be able to display the reference slide one more time?
Yeah, someone's talking on Zoom, but I think it's just muffled. Yeah, the audio quality of
Can you hear me? He asked if you could put the reference slide up one more time.
Oh, no, but the point is,
Hi, Grace.
oh, Grace. Yeah, so Grace, for some context, I gave a talk at 10 a.m. this morning, and I did not have time to update the references. So that reference slide is specifically delegated to neuromorphic language models. If you want that, I can bring it up, but it's not what you want to see. I can link. Yeah, if you're interested in following the lines of some of these papers, I'll just send them to you directly. Just shoot me an email.
They're great papers. Remember the bugs.
These are okay papers. Yeah.
In the slide where you said that you don't lose representational
Yeah.
capacity when you go from a full matrix, a dense matrix to a diagonal matrix, again, you didn't have an activation function there. All of that is lost if you have a nonlinear activation function there, right?
I'm not sure that it is lost.
If you go to the slide,
I'm really I know exactly what you're talking about, but I'm really scared of the delay on this slide deck. No, so truthfully, I don't think that. So applying nonlinearity doesn't matter.
it's gonna mix all of your so all of the eigenvalues of the matrices, right? It's gonna
An activation function. Activation functions are operated on these guys element-wise, unless it's softmax. But even with softmax, there's still a good amount of separation.
Let's say it's an H.
Yeah.
It's you cannot. I have to do math.
Yeah, let's think about it. As far as I'm concerned, the inclusion of nonlinearity just hurts your ability to train things in parallel. In that picture, for the most part, as far as RNNs are concerned, I now avoid applying nonlinearities through time. What I do is apply nonlinearities through space. So you would have seen the P D to the N times Q. Even though those are all linear, I will still apply a nonlinearity to P. I'll apply a nonlinearity to Q to preserve the universal function approximation theorem that the deep learning folk love so much. But the D, that remains as a linear token mixer so that everything can be trained very fast. So it's really a training. It's a byproduct of parallelization and training. Yeah.
And there's a question.
What do I think of the SynSense chip? What do you think of Inotera? We can talk one-on-one.
Well,
the question in the chat.
why one-on-one? Just
I don't know. it's such a high level question. I mean, it's very constrained in what you can do with it. It works very effectively. It's impressive that they've managed to get these cores that operate at microwatt scales. In practice, you could optimize the hell out of your SNN and enhance sparsity in order to go from 50 microwatts to 40 microwatts, but then your I/O is going to cost you half a milliwatt anyway, and that's going to dominate everything else. So yeah, it's I don't think it's overly necessary to optimize for sparsity in those cases. Initera, can't comment on them too much. I haven't used that shit before, so it would just be a misguided comment. There's another question.
I've also used the brain chip, the brain chips, Akita.
Akita, yeah, Akita definitely resembles a more prototypical accelerator more than the others, but they do bake in sparsity in there. And I see, yeah, Akita is definitely on a slightly larger scale than what SynSense's hardware is able to accelerate. As a result, it's in the single-digit watt regime rather than milliwatt, microwatt. As a function of that, yeah, you do see better latency measures, or you see improved latency measures relative to non-sparse models.
There was a question by Harrison earlier too, but how we skip.
So I'm confused on energy-aware learning. You reward the neural network for making the decision to not activate the EEG. No, you don't necessarily activate EEGs, rather, hey, that could be an idea. No, you're activating the neurostimulator. That was the dominant cost in the PD Parkinson's disease setup. You're not doing a binary decision on activate or deactivate. Rather, you're treating your pulse width, amplitude, and phase of your neurostimulator as free parameters that some Q-learning system can optimize. So you might start reducing your amplitude, and then you find energy as a surrogate of all of these values that can be calculated relatively straightforward. But then there's going to be a point where your stimulator is too low. And the other part of your loss function that says, hey, did the alpha beta power fall below a threshold? No. Well, now we're above the threshold, which in our case is a surrogate for there may be a higher risk of PD behavior. Therefore, we should probably increase the frequency a bit or increase the amplitude a bit. So it's really the parameterization of the neurostimulator that's being modified. And Krishna has asked, am I able to try surrogate gradient learning for spiking neural networks in our models? Leave that as the first part of the question. Everything trained on SNNcia uses surrogate gradients. Even with RTRL, one of those terms would implicitly have surrogate gradients in there. Potentially with any neuromorphic hardware. I haven't gone there. I haven't tried training on chip with surrogate gradients, largely because I think that what I've got available to me is not super efficient. However, there is some really good research by Charlotte Frenkel, the Reckon chip, presented at ISSCC, I want to say 3 years ago, which did implement a variant of RTRL on chip with models that are reasonably small, within the size of 128 hidden neurons. But hey, it worked really effectively, and that may be a direction to push in. But even with the work on RTRL applied to SNNs, I think very few people have actually realized that SNNs fit really well with RTRL. Just the matrix diagonalization thing is something that more so came from the deep learning crowd. The SNN folk were like, oh, we've been accidentally doing this the entire time. So it's been a good realization. Can I share the reference that I mentioned now for RTRL? Totally. I'll send you the name of the paper in the chat, or just a keyword to look up.
You listed already. There was a footnote already.
Not for the Reckon chip, but yeah, not for the Reckon chip, but the footnote would have been the original RTRL paper.
No, your paper.
Oh, I'm really scared to go back in the slide deck. It's just going to freeze my laptop. But yeah, I can take a look later. Yeah. I think everyone's absolutely tapped out.
I do have a question.
Please.
This is fantastic. And yes, if you mind going back to the previous slide. So it was
I'll cross my fingers. How far back do you want me to go?
Going.
So I think.
Hold on, you're a second. Stop. the reference that have your.
Oh, the energy aware learning stuff? No.
Keep going back, I guess. Going. One more. Here, this problem. Okay, here, this is, you made a statement here about the model capacity of what it can do. But in addition, what you just show here, you prove that people discarded this 40-year-old algorithm by Zipf-Cerebellium for the wrong reason.
Yeah.
Because you can always go, you do single validate position your state space.
Yep.
Diagonalize your matrix
and make it cheaper.
Everything. So beyond spiking neural networks, you can always take any recurrent neural network
and diagonalize it.
Diagonalize it
Exactly.
online, and then and you can make it super efficient.
Exactly. And so this deck, I think a small handful of you who have been to one of my other many UCSD talks. This comes from the original MatMol3 presentation, the MatMol3 language modeling paper, because that is an example of a model that is not a spiking neural network, but did rely on this diagonalization hack to make it more efficient and effectively get away with element-wise products instead of vector matrix mult. So
it's amazing.
It is. Yeah, it's people have been doing this for a while, right? Like, there's like 7 years of literature. Emre, of course, I think he was perhaps working on this in your lab as well, on RTRL variants with SNNs. And yet I didn't see a single paper from anyone that made this realization.
That's wonderful. So usually I've been waiting for this for 40 years. Thank you.
Close the loop in many ways now. Excellent. Does everyone want to go have a nap now? I'm really excited to have a nap.
A little side note, but there have been giants in the field here of deep learning.
Yeah.
Jeff Hellman, after whom many advances in recurrent networks were also identified.
Yeah.
He co-founded the Hallucilu Data Science Institute together with Roger Slutta.
Yeah.
He passed away, unfortunately, but there's a great legacy here of the US putting all this algorithms, and this fits in beautifully. It's great.
Wonderful. No, I'm glad to serve. Cool.
More questions, or should we go to more backlog and more team?
Vikrant, you look like you have a question. You look like you have more of a comment than a question.
Definitely not that.
Yeah, awesome.
Tell us more about neuromorphic neuromodulation. What is the future?
What is the future of neuromorphic neuromodulation? Having a nap. No, I mean, closed loop systems, I think, are one of the biggest places where anything neuromorphic flavored is going to be relevant in. I do have this kind of mantra of personal self-skepticism in a lot of the work that I do. And I hope that that is made clear by consistently asking, does it make sense to use SNNs here? Because you're often not getting the win that you bargain for when you apply a cheaper model. And quite often, the model that you use isn't determinative of the final system energy, right? You really have to treat everything holistically. And I think that, I don't know, neuromorphics might take little pieces of the brain, spikes, dynamics, sparsity, event-based computation, and say, sick, we've got a fantastic model that's able to do something really efficiently. And there's a few other neuromorphic folk that are looking at embodiment and sensing, actuation, etc. But then when that actuation and the sensing are going to exceed the cost of computation, doesn't it make sense to lift your computation just a little bit to make your actuation a little bit cheaper? And so I think that that is a really critical place in the neuromodulation space, and perhaps even in the context of just running large language models, right? That's where I'm placing my personal bets. Do my bets win? Don't know. We'll see. My stocks have done pretty well lately. Diversified index funds, so maybe this is also a place to go.
There's one more question on Zoom. In fact, the same question I asked this morning.
Any advice or request for new variants of neuromorphic chips, particularly for working with LLMs? is my morning talk going to be recorded? What was it? Is it going to be uploaded?
Yes.
That's probably a really good place to go to. I'll give you a 1 hour answer. Can I give you an answer in 15 seconds? My finding so far is that having a single chip to make everything better in specifically LLMs doesn't exist yet, because LLMs are fundamentally very heterogeneous in their profiles. Prefill, decode, attention, feed-forward nets, single-tenant, multi-tenant use cases. All of these are going to be somewhat variant in their bottlenecks. Some of these are memory-bound processes, some of these are compute-bound processes, some of these will benefit more from activation sparsity, some of these benefit more from weight sparsity. So I think that the way to go is identifying under what cases what your different bottlenecks are, and then optimizing for that. And if you really want to try and magic a silver bullet for everything, then yeah, let me know if you find an answer, because I'm not sure.
We have Eugene in the audience. You can
Oh.
say a bit more about this too. Right?
Oh yeah, yeah. Go for it, Eugene. I'll let you take the next hour of presenting.
All right.
All right.
So much. Yeah, let's get it.
Y'all can go to bed now. Because same.